All right, we're in unit number 6, conservation of energy, page 6 of your notes, and we're going to work through example number 2. Let me zoom in just a little bit and work through this. All right, example number 2. It says an intelligent student, I'm sure a physics student, decides to drop his or her 600-gram English book off of a 12-meter cliff to study the law of conservation of energy. Obviously, you would not want to drop your physics book. English book's perfectly fine to drop. So fill out the chart below. All right, so here's our cliff, and I don't have a real good picture of a book there, but you get the idea. And so we have this book that we're dropping, and at part A is 12 meters above the ground. At part B, it's 8 meters above the ground. And part C, it's 4, and then part D, it's on the ground. And so what we want to do is we want to calculate the kinetic energy at A, the gravitational potential energy at A, and then the mechanical energy at A. And we'll talk about the mechanical energy in just a bit. So the easiest thing to do is actually calculate the gravitational potential energy. I'm going to go ahead and do that for the first one, then you can stop the video and do the calculations a little bit on your own. I'm not going to show all of them here, but let's run through the first one. So we're going to do gravitational potential energy. Zoom in here at A, and so that'll be mgh. The mass of the book is 600 grams, which is going to be 0.6 kilograms. The acceleration of gravity is 9.8 meters per second squared, and it is 12 meters above the ground. So let's go ahead and plug all of that in. So I got 0.6 times 9.8 times 12, and that gives me, we'll say just round it off to make it easy, it's basically 7, oh, we'll be accurate, 70.56, and that'll be joules. All right, so I'm going to go back over to my chart and plug that in. So 70.56 joules. All right, now you just go ahead and quick stop the tape and go ahead and calculate the gravitational potential energy at the rest of them. I'm going to go ahead and kind of do that quick on the side here and fill them in. So this one is 47.04 joules. Next one's going to be 0.6 times 4 times 9.8. That's going to be 23.52 joules, and then this is going to be 0 joules. All right, so that's gravitational potential energy. Notice what happens to the gravitational potential energy. Well, as this falls, it gets closer. Remember, we're assuming the reference point is going to be on the ground. It gets closer to the ground, and so if it gets closer to the ground, then gravitational potential energy should go down. And as soon as it's on the ground, since it's on the reference level, then it should be 0. And that makes sense. Okay, the next one that we're going to do is calculate the kinetic energy at each point. So the kinetic energy at the top is easy. The rest of them are not as easy. So we're going to go 1/2 times the mass, which is 0.6 kilograms, times the speed. Now, it's at rest at the top. It's at rest at the top. So that makes this calculation very, very easy. So it's 0 joules. But what about B? Well, to do the kinetic energy at B, I have to know how fast it's moving. To figure out how fast it's moving, I have to do the big 3. So I'm going to do that for letter B, show you how it's done. You can stop the video, work it through for the rest of them. But here's how you do it for letter B. So I got D, VO, VF, A, and T. And let me pull that out just a little bit. All right, so this is at B. So D would be how far it's fallen, not how high it's above the cliff. So there's a difference here. H in this case, way down here, is how high you are above the cliff, but this D is how far you've fallen. And in this case, we've fallen 4 meters, negative because we're below where we start. We started with an initial speed of 0. We're looking for this one. A is going to be negative 9.8 meters per second squared. And then time we obviously don't know. So we have to use a big 3. And the big 3 that we're going to use, I'm trying to find room here. So we're going to do VF squared equals VO squared plus 2AD. There's the 0. VF is equal to plus or minus the square root of 2AD. VF is equal to plus, actually minus, because we're going down, square root 2, and I'm running out of room here, negative 9.8, let's see, meters per second squared, times the distance, which is negative, I think we said negative 4. Alright, let me plug that in and get the answer first. If you need to stop and check out what I've got there, that's fine. Here it is here. So I'm going to take the square root. I'm doing 2 times 9.8 times, and we said, I think, 5. Now, I can throw in the negative there with the 9.8. I can throw it in with the 5, but I know the negatives are going to cancel out when they're multiplied together, so I don't do that on my calculator. And then I get the speed of we'll say 9 meters per second squared. I have to bring this negative down. This one doesn't get canceled out. So there's the speed. All right, now I can use that speed. That's the speed at B, right up here. So I can use that speed with the kinetic energy equation to figure out the kinetic energy at B. Almost feels like a vicious circle. So kinetic energy equals 1/2 mv squared. Kinetic energy equals 1/2 times the mass, 0.6 kilograms, times V, which is negative 9.9 meters per second squared. And then here we go. So 9.9, it's squared. I'll show it here so you can see it. Again, I mean, you can throw in the negative there and square it, and that's fine. I know that negative is going to be squared out, so I don't include it on my calculations. So I'm going to go ahead and square it, multiply it times 0.6, and multiply it times 0.5. And I get 28.812. So 28.812, and that'll be measured in joules. So I'm going to include that back up here in my table. So 28.812 joules. Alright, now I'm just making sure I didn't make a mistake, because I feel like I made a mistake. Did I do this right? Making sure I didn't make a mistake. I'm going to double check my calculations real quick over here. So it's 2 times 9.8 times, I think we said 4 meters. Yep. I'm going to take the square root of that. And, I did make a mistake. Let me double check that one more time. Earlier I calculated 9.9, and on this one I'm calculating 8.85. So let me do that one more time. So I'm going to take the square root of 2 times 9.8 times 4. I'm sure if you were watching the video, you probably caught it earlier and found my mistake. 8.8. There it is. So 8.85, which is going to change my previous answer. So let me go back over here. So that's going to change this one. Sorry about making this mistake. Glad I caught it. 8.85. I'm going to square that times 0.6 times 0.5, and I get 23.52 joules. Which I can back up here. Change that one. Making mistakes is not a bad thing. You just got to find them as you're going through. So 23.52 joules. All right. Now, let's see what we've got going on here. Mechanical energy. We went through the definition of mechanical energy several videos ago, and if you don't remember, mechanical energy is one of 4 different types of energy. Kinetic energy, gravitational potential energy, rotational kinetic energy, and then spring potential energy. Well, we don't have spring potential energy in this particular example, and we don't have rotational kinetic energy in this particular example, so we don't have to worry about those. So when I want to calculate the mechanical energy, it's basically kinetic energy, gravitational, and potential energy added together, and that gives me mechanical. So if I just add across, that'll give you mechanical energy. So 70.56 joules. There's that one. Let me add these two together and see what I get. So here's my calculator. Come up underneath. So 23.52 plus 47.04. And if I did this right, you're going to notice something kind of cool pop up. Oh, what do you know? Look at that. Do you see that those are the same? What's going on there? Well, it's what we talked about earlier. Your energy, in this case mechanical energy, is being conserved. As the object drops, let me kind of put this all in here, as the object drops, its gravitational potential energy decreases and its kinetic energy goes up. So you could think of it as this. Any gravitational potential energy that you lose gets transformed into kinetic energy. That's kind of what's going on. So gravitational potential energy lost 23.52 joules from A to B, and kinetic gained that 23.52 joules. And the mechanical energy on the way down stays the same. There's your conservation of energy. In this case, it's conservation of mechanical energy. Kinetic wasn't conserved. Gravitational wasn't conserved, but mechanical was. And that's going to be an important concept as we move forward in this chapter. Mechanical energy, in a lot of cases, will be conserved. Now, not all cases, and we'll talk about those, but in a lot of cases it will be. So, on the way down, we can say that mechanical energy will always be 70.56 joules. And then we can save ourselves some time instead of going through all of this to get the kinetic energy here and the kinetic energy here, add it to the gravitational potential energy and find out that it's going to be the same. Well, we can just make that assumption. I'll tell you why we can make that assumption in a bit. Make that assumption and work it backwards to get the kinetic. So if I take this guy, subtract the 23.52, I'll get 4704. And you can verify that on a calculator if you like. There it is there. And then if I subtract those, it'll be 70.56 joules. So look at what's going on here. At the bottom, when it hits the ground, it has a bunch of energy because it is moving when it hits the ground. A lot of people think it's at rest when it hits the ground. Well, it comes to rest, I'll give you that. I agree with that. But when it hits the ground, it's still in motion. And if you didn't believe that, if you don't believe that, then take a book, climb to the top of a 12-meter high cliff, take a rock, whatever it is, you lay down here, have a friend drop it on you. If you believe that it's going to be at rest when it hits the ground, then you'll be just fine. But you instinctively know that that object is going to be in motion when it hits the ground because you wouldn't want to lay down there and be walloped by it when it hits you. So it is in motion when it hits the ground. All right, now I've got down here below a demonstration that I do in class. I can't really do this one in class with beakers and super balls, so you have to kind of attend class to get that one. I apologize for that. But I do have a super ball right here, and this is my next demonstration. So I just have a normal super ball that basically bounces. And so let's take a look at what's going on with this. This super ball that's bouncing is no different than the ball that we have up here. When I let go of the ball, it has gravitational potential energy at the top, and as it falls, it switches, transforms that that gravitational potential energy kinetic on the way down. So it bounces back and forth. Now I've got a question for you, and you can't really see this on the video, but as I drop this ball, it doesn't go back up to the same height. I mean, grab a super ball. A lot of people think that super balls always go back up to the same height, but they don't. There isn't one that has been created or made or manufactured or that can be made or manufactured that will come back up to its original height. For example, if this was a super ball, you can drop it up here and it'll go down, hit the ground, and come back up to here. Or it'll come back up to here, but it'll never reach the original height. And the question is, well, why isn't it reaching that original height? Well, when it hits the ground, there's some energy that's being some of that kinetic energy is transferred into sound and thermal energy. And the process of transferring into the sound and thermal energy, this is what this example is all about, it loses energy, or better way of saying it is transfers some of that energy into thermal and sound. That way it won't have as much energy to go back up and then it won't go back up to its original height. A great example of that is this super ball. This one's not the same one that I've been dropping. Notice this, watch this one. It doesn't bounce. This one bounces quite a while. But this guy here, basically no bouncing. What's going on? Well, they're slightly made of different materials. You can see this one's a little shinier than this one. And it's also a different sound. I'm not sure if it's going to pick up on the video real well, but now listen to this one. When you're hearing it live in the room, this one's much louder. So when it hits the ground, its energy, any energy it has, is quickly, or nearly all of it, is transformed into sound and thermal energy. This one still retains some of its kinetic energy and can bounce back and forth for a little while. It does come to rest. So let's talk about conservative forces then. Conservative forces are forces such as gravitational potential energy and the electromagnetic force, we'll talk about that one a little bit next year, that produce movement without transforming mechanical energy into thermal energy, and thereby preserving the law of conservation of energy. So I think this graph down below will be helpful. So we're going to sketch gravitational, kinetic, and mechanical on an energy time graph, assuming conservative forces. So we're going to take basically an object, let it drop once, and sketch what's going on with the gravitational potential energy and the kinetic energy and mechanical energy. Let's do gravitational because it's the easiest. So at the top of the, when I let it go at the very top, I have a lot of gravitational potential energy. And as it falls, that gravitational potential energy goes down. When it hits the ground, it has 0, and then on its way back up, okay, it gains its gravitational potential energy back. So as long as the forces are conservative, which means we're not producing thermal energy, we're not producing sound, we can get back up to where we start. You can recoup, you could say, all that gravitational potential energy. So if you dropped it at 12 meters, it'll come back to the 12 meters. Now, that doesn't happen in reality. We'll talk about that why in just a bit. Now let's talk about kinetic energy. Well, at the top, the kinetic energy is 0 because it's not in motion. But as it falls, the kinetic energy increases, gets all the way to the top. That's when it's moving gets all the way to the bottom. I said top because we're at the top up here. Gets all the way to the bottom when it's traveling the fastest, and then on its way down, its kinetic energy decreases. On the way back up, the kinetic energy increases. Notice what's happening in kinetic and gravitational. They're always opposite one another. As gravitational potential energy is decreasing on the way down, kinetic energy is increasing. At the top, there's no gravitational potential energy, but there is a lot of kinetic energy at the top. And that's where it's maxed out. On the way up, the kinetic goes down and the gravitational goes up. What's happening to the mechanical energy? Well, look at what's happening to the mechanical energy up here. Mechanical energy is always the same. It's really the sum of the two energies. So the mechanical energy would be a line going right like this. And that would be your mechanical energy. It's always the same all the way through. Now, in class, I actually we'll have a bowling ball suspended from the ceiling, and we'll swing it back and forth, and you'll actually see, and we'll do a motion probe, we can actually chart the kinetic energy, and as it swings back and forth, its kinetic energy is basically going to swing back and forth, which would be kind of cool. Alright, flipping it over, let's talk about non-conservative forces. These are forces that cause a loss in total mechanical energy. An example of a non-conservative force is going to be friction. So when we have friction involved, the graph won't look like this anymore because we're going to produce some thermal energy and we're going to produce some sound. So what will that graph look like? Well, gravitational potential energy will start high, it'll go down just like we had, but it won't go back up to the original height. It'll fall a little short. And then it'll go down, hit the ground again, fall a little short again. Kinetic energy is going to be doing kind of the same thing. Kinetic energy It's going to go here, and it'll never reach the top. And what will happen to the mechanical energy is slowly, and eventually both will be zero. And you can see that right here. If I drop this ball and it doesn't roll off the page, it'll come to rest. It'll come to rest because both of these energies, let's see if I can do this well. There you go. Both of these energies will be at zero. It'll have no gravitational potential energy because it's on the ground, and its kinetic energy will be zero because it's at rest. All right, I think that's it. We'll start with energy transformation diagrams in the next video.